Hello everyone, my name is Robert Strandh, and this talk is about representing method combinations. The context of this work is the SICL project, and I will just give you the link and you can read more about it yourself. I'm not going to mention anything more about it today. A generic function is a feature of object-oriented languages. You can think of a generic function as a collection of methods that share the same name. In most object-oriented languages, a generic function is not a first-class object. However, in Common Lisp it is, because it's an instance of a subclass of the class function. In traditional object-oriented languages, a generic function is invoked by putting an argument followed by a dot, followed by the name of the generic function, followed by the remaining arguments. In Common Lisp, we invoke a generic function just like we invoke any other function, followed by the arguments. Now, because of subclassing, such an invocation may result in several methods being applicable simultaneously. In traditional object-oriented languages, only the most specific applicable method is invoked, and if the programmer wants less specific methods to be invoked as well, that would require some kind of explicit call such as super or the equivalent in that programming language. And if the programmer wants to combine the results of several of the invocation of several different applicable methods, that requires explicit code. In Common Lisp, on the other hand, the applicable methods are combined in some way, and this combination is expressed as a lambda expression called the effective method. The effective method contains calls to the individual methods, and the compiler is called in order to turn the effective method into an effective method function. And when this effective method function is applied to the arguments of the invocation of the generic function, the effective method function calls these methods in the right order according to the combination that was chosen. How these applicable methods are combined is defined by a function called compute effective method. And this generic function has three parameters: a generic function metaobject, a method combination metaobject, which is the important thing here, and a list of method metaobjects. And a call to this generic function returns an effective method. The role of the method combination metaobject is that it designates a method combination procedure. That is, it designates some kind of function to combine the different applicable methods. And this procedure can be implemented in different ways. It can be a method on this generic function, compute effective method, specialized to some kind of method combination class, or it could be a function stored in the method combination object, or possibly any other way that will accomplish the same task. And there's very little said in the Common Lisp standard about method combinations. What we know is that there is a system class called method combination. We know that method combination metaobjects must be indirect instances of this class. That is, they cannot be direct instances of this class. That has to be a subclass. And we know that a method combination metaobject contains information about its type and the arguments used with that type. And I'll get back to that later. So here's an example of how to use method combinations in Common Lisp. This is the definition of a generic function called foo. And it has an option called colon method combination. And the that option is followed by the name of a method combination type, which in this case is AND, followed by some arguments, method combination arguments that are accepted by this particular type of method combination. And in this particular case, all the applicable methods are combined using the AND operator. And the arguments to the AND operator are the results of applying each applicable method to the arguments of the generic function. The defined method combination operator in Common Lisp is what's used to define method combination types. And it has two versions, called the short version and the long version. These are not called versions in the standard, they're called forms, but we do not want to confuse it with form as in expressions to be evaluated. So I'm calling them versions here. The short version looks like this: define method combination followed by a name followed by options. And the options here are unimportant for this presentation. What's important here is the name. So it defines a method combination type that has that name, and it accepts one optional argument that can be either most specific first or most specific last. And if no argument is given, it defaults to most specific first. The long version of define method combination looks like this: define method combination name, and then it has a lambda list followed by some information that we don't need to know for this presentation, followed by a sequence of forms in the function body. The lambda list here is an ordinary lambda list, and it specifies what kind of arguments can be given after the method combination option to the def generic form. For the purpose of this work, we are interested in a couple of scenarios, and we want to be able to define exactly what happens in those different scenarios. So the first scenario is the user defines a method combination type using define method combination, then uses that type in a def generic form, but makes a mistake in the arguments, that is a typo or something like that. Clearly what we would like here is to have a warning issued that says that these arguments are incompatible with the method combination type that has the name that was chosen. And we also want an error to be signaled if an attempt is made to invoke the generic function that was defined in this incorrect way. The scenario number 2 is that the user defines a method combination type using the long version of defined method combination, but makes a mistake in the lambda list. Then the user defines def generic forms with the intended arguments, which are then incompatible with the ones that in the lambda list of defined method combination. What we would like then, of course, the warning we would like for the warning to be issued as soon as possible, saying it's incompatible. And then, of course, the programmer or the user will reevaluate the defined method combination form, and we would then like to, for the def generic form that was evaluated before, to now be valid again. The third scenario is the user defines a method combination type using the long version of defined method combination, then uses a def generic with the acceptable argument, so everything works. But later the user decides to change the lambda list in the defined method combination form, and thereby redefines the method combination type. We would then, of course, like to have warnings that say the following generic functions now have incorrect arguments to this particular defined method combination type, and allow the user to correct those generic function definitions. With respect to those scenarios, we have had a look at several different FLOSS implementations. FLOSS means free and libre open source software. We first looked at portable common loops, which is not a Common Lisp implementation. It's kind of a library that is used for adding CLOS to a pre-ANSI Common Lisp implementation. We looked at SBCL, we looked at CCL, and we looked at ECL, and also CLASP, but CLASP is really the same as ECL in this particular respect. Many of them failed several scenarios. All of them sometimes fail to verify the validity of method combination arguments early. That is, they do not report the incorrect arguments when the def generic form is evaluated. Instead, they're evaluated when an attempt when there is an attempt to use this generic function, which would then call compute effective method implicitly. And that can result in very cryptic messages, such as incompatible lambda list for this particular function that the user has forgotten about a long time ago. And the details of these investigations can be found in the paper. We are not going to talk about them anymore here. This graph shows how we organize our classes and instances in the technique described in our paper. So we have metaobject being a superclass of method combination as the AMOP book stipulates. And then we have standard method combination, which is a subclass of method combination as the standard suggests. It doesn't suggest a name for it, but it's a typical name. And these are instances of method combinations. So these are the method combination meta objects. They are versions, let's say, of method combination templates or types. And I've shown two types here: the standard method combination, which has a single variety, and the AND method combination type that has two varieties to it, most specific first and most specific last, according to the arguments that were given. So as we can see here, the method combination meta object stores the arguments to the particular method combination type that was chosen. And what we don't see here is also the method combination template contains a list of varieties for it, so that we can reuse these method combination meta objects when the same arguments are used later on. We do not cover all the scenarios in this talk. The details of all the scenarios are in the paper. The only technique we report here is the detection of incorrect method combination arguments, and we want that detection to be done early. And this is where most implementations fail sometimes. So to see what we do, recall the long version of defined method combination looks like this: defined method combination name, lambda list, stuff we're not interested in, and the body. And the lambda list, as I said before, is an ordinary lambda list that specifies what arguments can be given after method combination option to def generic. What we do is we translate the short version to the long version. Not every implementation does this. Some of them have subclasses of standard method combinations specific to the short version and the long version. We analyze this lambda list here, and extract all the parameters that can be used in the body. These are either the required parameters or the optional parameters or the keyword parameters. From this analysis, we construct a lambda list as follows, or lambda expressions are as follows. Lambda list of all these variables that we extracted from the lambda list. And this is the original lambda list given to the defined method combination form. We compile this lambda expression to obtain a function. When this function is applied to the method combination arguments, it returns this list of objects that can be used to identify a particular method combination metaobject of a given type. We use this list for recycling existing method combination metaobjects. In our defined method combination forms, we include aux parameters that have initialization expressions that verify the arguments. So for instance, if we were to use the long version of defined method combination in order to define the AND method combination, we would specify this optional parameter called order, which defaults to most specific first, as we mentioned before. And if we look at the Common Lisp hyperspec, that's all that is specified here, which means that there is no verification that the optional argument is either most specific first or most specific last. We fixed this problem by introducing this aux parameter that here is called ignore, and an initialization form that checks that the order is a member of this list of the two. So when our constructed function is applied to some incorrect method combination arguments, it may fail because the arguments are incompatible with the parameters of the lambda list. For instance, we might give too many or too few parameters, or we might give a keyword parameter that's not acceptable. Or it may fail because one or more of the initialization forms in the aux parameters call error. And in both cases, we handle the error and report incorrect arguments. So this is our way of early report of incompatible arguments to the particular method combination type. Now, for future work is that we need to incorporate this technique into SICL. We designed this technique after we had started work on the method combinations in SICL. This technique that we describe here could benefit from some weak data structures because they hold on to generic function meta objects that need to be redefined when the lambda list of a method combination type is modified. And of course, if these generic function meta objects are discarded by a call to fmac on bound or something similar, then they are held on to by the data structure that we described here. So a weak data structure would be useful in this case. So to finish, we would like to acknowledge some people for reading valuable feedback on early versions of this paper. Thank you very much.